Welcome to Chapter 24, Comparing Means. So in the last chapter is when we started looking at means of a group. The example we did in class was the different amounts of coffee that were in coffee cups. So we were just looking at that one sample of 20 coffee cups. Well, now we have two different groups that we are looking at, and we're going to compare the means between them. So just as we compared proportions to each other, what we are most interested in is the difference between the two groups. Okay, and most experiments do actually end up being between two different groups. We want to know, we'd have a control group and we'd have the experimental group, and we want to see how did the experimental group react to maybe a new drug or some sort of treatment in comparison to the control group that had no treatment or drug given to them. Okay, so most often you're going to see experiments done between two groups. So comparing means is very important as we continue on with our hypothesis testing. So we haven't looked at dot plots or box plots in a while, but when we're comparing two groups such as this, we want to use box plots. And if I need to show you again how to do that on your calculators or Google it or look back through your notes, you will end up needing to look at comparing box plots. Okay, so the two box plots that you're looking at is the differences between a brand name of batteries and a generic name of batteries and how long they last. Okay, so we can look at what the duration is between the two groups and see that they are definitely, in fact, two different groups. If these box plots look the same, well, then there would be no point in even being able to do hypothesis testing with the difference between the groups, because there wouldn't be a difference. So that's what we're looking for here, to make sure that there is some sort of difference. Okay, so once we've looked at the side-by-side box plots, then we can start to compare the two means to each other. So same idea as if we were comparing proportions, but now we're comparing two means. And remember, the mu, this symbol, is the mean for a population. Okay, or the parameter of interest. Okay. So for independent random quantities, we add the variances together, and the standard deviation is no different than that. We did this before when we were comparing two proportions to each other. So we have the difference between the two standard deviations. We square the standard deviation to get the variance, and then we take the square root of the whole thing because we eventually want the standard deviation between the two of them. Okay, so it's exactly the same process, but remember, we don't know what the standard deviation is, so we have to use S for the standard deviation of our sample, and we're going to be calculating the standard error. So these are the next two that you are going to be looking at on your calculator. So I just want to make sure that we understand that when you're saying this is the test I'm using, you need to be very particular about what test you're actually using. So with the confidence interval, and I will give you another formula sheet, it says 2 sample t interval because there are two samples. We're using a t-test and we're finding a confidence interval. With hypothesis testing, same idea, but we want the 2 sample t-test. So none of this should be brand new. These are very similar formulas to what we did with proportions, but now we're talking about means. Okay, so the difference between the two means, here are the means for the one group, and here are the means for the other group. Okay, so we're just going to, the standardized sample difference between the means of the two independent groups, here's exactly what we're looking for. Okay, these are the means between the two samples, and this is what we expect to have happen. Typically, the difference in the population is going to be 0. So I realize that this all looks like a lot here, but usually, and this is on a few slides later, you're going to see that the difference in these means are going to be 0 because what we want, our hypothesis is going to be that there was no difference between them. And that's what we're testing. The difference between the groups, and then the fact that we don't think there really was a difference anyway. Okay, the degrees of freedom is a special formula that we are going to be looking at, and the calculator is actually going to figure this out for us. Okay, all right, so we estimate the standard error right here. Okay, so same as we did before. N1 is the number of the sample, or how many people are in sample 1, and N2 is how many people are in sample 2. Okay, but I'll get back to degrees of freedom. All right, so with our assumptions and conditions, okay, so again, the condition needs to be checked for each group. Okay, so whether it's randomized, again, these are similar to what we've done before. 10%. Don't usually check this condition for the differences of means. We check it for the means only if we have a very small population or an extremely large sample. But typically you're not going to have to check that. A nearly normal condition, so it must be checked for both groups. So you'll run a histogram for each group independently and see what they look like, and make sure that there are no outliers. Make sure that the histogram is not skewed in one direction or the other. Okay. All right, so the two groups that we're comparing, they must be independent of each other. And the next chapter will be talking about if they're not independent. So please make sure that they are independent of each other, which means that they are not from the same group. They're different. Okay. So with the battery example, we're not comparing batteries within the same group of generic brand. We're comparing generic to store brand, or to a name brand. Okay, so those are two independent groups because they have really nothing to do with each other. They both have batteries, but we're testing the type of battery that they are. Okay, so for our 2-sample T interval, so once the conditions are met, remember every time you're doing a confidence interval or a hypothesis test, then you must check all of those conditions. So if you didn't make a list of what those conditions were, go back, rewind the video a bit, and then make sure you write those down, just what the differences are here. Okay? All right, so y bar 1 minus y bar 2, this is the difference in the means between the two groups. The degrees of, plus or minus the degrees of freedom times the standard error of the difference of the two groups. So some people were confused before. This whole formula is right here. Okay, so you will solve this and you'll substitute it in here. So actually this is what you're solving, and then that goes right in there. This is the standard error between these two groups. Okay. All right, so the critical value depends on the confidence level that you choose and that you specify, and on the number of degrees of freedom. And we get from the sample sizes and the special formula that we use. Okay. All right, so here is the really ugly formula. So before you get too excited about this, we're not going to be using this. You're not going to be memorizing this. You're not going to be using this. Look, it says right here, it's a bear. We're not doing this. You will be using your calculator to figure this out. Okay, so there are going to be a couple of little different things that we have to do with the calculator, but you're going to let the technology calculate how many degrees of freedom there are. And remember, we need the degrees of freedom to figure out the p-value. So that's why this is coming back. When you use the TCDF, you need to include how many degrees of freedom there are. So we need to do something in order to be able to figure that out. So we have the p-value. Okay. All right, so when we're testing the difference between the two means, okay, so it's the 2-sample t-test for means. The conditions for the 2-sample t-test is the same for the 2-sample t-interval. Okay, this is what I was talking about. So the difference in the means, remember this is before there was any sort of treatment. Okay, so our hypothesis is that there is going to be no difference between them. So this delta 0, delta means the change of. So delta 0 means that there typically is no difference. So really the delta just means what is the difference, but typically it's going to be 0. Okay, so we're comparing the sample means, right? We're subtracting those from each other minus most probably 0, and we divide that by the standard error. Okay, so this is very similar to the z-score that we've done before, and the t-score that we just looked at in the last chapter. Okay. All right. So you might be wondering, well, with proportions, we pooled the data, but with t-tests, it doesn't seem like we've talked about pooling the data at all. We are not pooling the data. It gets very complicated, and we're not sure if the variances are going to be the same, so we don't pool. And this is all over your book. This is in lots of other AP statistics that I found, that the difficulty with deciding whether to pool or not is too great, so we are not ever going to pool. So do not pool, not pooling data, okay? All right, so just very quickly, what can go wrong? So we want to watch out for paired data, okay? So if the samples are not independent, so if they are dependent on each other, then you can't use two sample methods, and those will be other methods that we'll talk about. So look at the plots. I will show you how to look at box plots. If you could take the time to figure out how to do that, refresh your memory. It's really just in the second y equals again, and then you would just choose box plot. Okay, so you just have to pick the different lists when you put the data in. Okay, so make sure that you have looked at the plots. Okay. We've learned to use statistical inference to compare the means of two independent groups. We use t-models for the methods in this chapter, so you're checking your conditions and you're using the standard error. We're not ever pooling. Okay, so the same idea, the same 4 steps that you've been doing with hypothesis testing are exactly the same. It's just the wording is different and the mechanics are different. So let's go through an example. Okay, so I don't know where the first page of this went. Okay, so we have two generic, oh, that's right, we started off with this. So judging from the box plots that we already saw, so we're going to compare the generic batteries to brand name batteries. Okay, the generic batteries look like they last 20 minutes longer because of where the box plots were. But before we change anything, we want to know what we expect to happen with the next batteries that we buy. So how much longer might we think the generic batteries last? Okay, so on the left here, we can check off our different conditions. And before I get too into this, my suggestion is that you be making notes as we go through this example. So this is a great time to stop the video and be able to, or pause the video and write down what these conditions are. The calculations that I'm going to be doing involve the set of data from the brand name and also the set of data from the generic brand. So practice putting the brand name in list 1 and generic in list 2, and then as we go through this, that might make all of the work that you need to do a bit easier once you have that in there, because you can do the problem with me. Okay. All right, so back to this. So randomization condition. Batteries were selected at random, not exactly a simple random sample, but it's reasonably random. All is good. Okay, the batteries, even they were packaged together, so they might not be independent. A storage problem might affect all the batteries in the same pack, and repeating the study for several different packs of batteries would make the conclusion that much stronger. Okay, because if you're taking a pack of batteries and you're testing all of them, then they're from the same pack, so they could have all been, they have I guess, an equal chance of being damaged. Okay, independent groups assumption. So the batteries are manufactured by 2 different companies and they're purchased in separate packages, so that is all good, and that shows that they're independent. And the nearly normal condition, we look at the 2 histograms, and they're not too bad. The samples are small. The histograms look unimodal, which means they have one mode, and they are symmetric. So they look pretty similar to each other. Okay, so lots of information on this next slide. Always a good idea to write down exactly everything that you know. Okay, so from the calculator, you do you're going to calculate both of them. So before, instead of 1 var stats, now it's 2 var stats. Okay, so L1 and L2 are your 2 stats. Okay, making sure you're paying attention to what you just found and which list you put them in is important. So Y bar generic, 206 minutes, and the S of the generic is 10.3 minutes. And then here we have the information for the store brand, or I'm sorry, I keep saying that, for the brand name. Okay. All right, so before I get to using the technology, so the groups are independent, so we'll just plug everything into the formula. Okay, remembering to square the standard deviations divided by 6 because there are 6 batteries in each group. Okay, and we come up with 7.29 minutes is what the standard error is. Okay, so if you are using a TI-84, you'll do the second stat, and you'll arrow over to where it says tests. Okay, so stats, arrow over to where it says tests, and you're going to arrow down to where you see 2 sample t interval. There's also 2 sample t tests, but we want 2 sample interval stats, or 2 sample interval, I'm sorry. Okay. All right, so the difference between data and stats, if you have the data in the lists, you don't need to, then you would click on data and make sure that's highlighted because the calculator will then use the data from the lists. If you just have the stats, okay, so that's what I did for this example. I had the stats and then I inputted all of this information. So X1, this information right here is coming from here. And this information is coming from here. Okay, all right, we're not going to pool. And you arrow, there's another arrow, so you go down one more. It says calculate. And when you click that button, it pops up with here is your confidence interval. And we'll get back to that. And here are your degrees of freedom. So over on this side where it says this is from technology, well, this is how it got figured out. Okay, you input this data and then you push enter and calculate, and it calculates the degrees of freedom for you. All right, and here's your interval. Now on the AP test, they do want you to write this out as well. Okay, so the corresponding critical value for a 95% confidence interval is 2.263. And that can come either with the inverse t, you could calculate that, or off the table. Either way, you can get that. Okay, so this can be inverse t. Okay, and the 95% confidence interval. All right, so here's the margin of error. So we just figured out what the standard error is. Okay, and here's the t interval. And then this is what my final answer is, which matches with what the calculator calculated. Okay, so if you haven't had a chance to write down how to say this, now is a great time to put that in here. So I'm 95% confident that the interval from 2.1 to 35.1 captures the mean amount of time by which the generic batteries outlast brand name batteries for this task. If generic brands are cheaper, there seems little reason not to use them. If it is more trouble or costs more to buy them, then I'd consider whether the additional performance is worth it. So I am confident that the true number of minutes is between 2.1 and 35.1. Okay, and then that's it. That's what you have to do. Okay, tomorrow in class we'll go through how to use a t-test. Okay, so make sure this example is written down, and using technology you have that as well. All right, that's it. End of chapter 24.